This course is about fundamentals in physics, but before we study these fundamentals, let us start with this very important question. What is physics? We have a couple of definitions. Our next closest ally after Google when it comes to information seeking, Wikipedia, describes physics as a natural science that involves the study of matter and its motion through space and time, along with related concepts such as energy and force. We also have definitions taken from Oxford and Merriam-Webster dictionaries and one from Encyclopedia. Now, as you read through these definitions, I hope you realize that this definition mentions a couple of things consistently, a strong indication that they are important. First, it is the study of something which is material or physical in nature. And because it is material, it is measurable and quantifiable. This is important, as this definition establishes physics as an empirical science. That is to say, it has to be based on evidence or data acquired through sound scientific experiment or observation, as in some area of physics, such as astronomy or cosmology, conducting an experiment is nearly unfeasible. Mathematics, for instance, is not an empirical science because it does not base itself on experimental evidence. It based on a set of axioms defined by mathematicians, and from this set of axioms, theorems and lemma are derived logically. Now, one could come out with a set of logical and some theoreticians like to say beautiful mathematical equations in the attempt to describe a phenomenon. Unless these equations stand the experimental test or observation over time, unless these equations are able to predict the experimental result correctly, well, no matter how beautiful or neat these equations are, they are just mathematical equations. For that reason, we involve practical session in this course, so that you guys are able to test for and hopefully convince yourself that the equation you learned in class are physics equations. Second, it is also the study of how these quantities are interacting, and they are interacting through exchange of energy and force. Force and energy are some of the fundamentals we are going to learn in this course, so we will be talking more about them in subsequent lectures. Another point worth highlighting is that physics reigns in the realm of observable universe. Astrology or spectrology, the study of ghosts and spirit, for example, are not physics, simply because the subject they are studying are not observable, not in the same sense as how you will observe object falling down due to gravity. And talking about observable universe, this begs for another question, isn't it? That is, what is considered as the observable universe? How small or how big is this observable universe? And if this observable, we should be able to put numbers to it, shouldn't we? As a matter of fact, yes, we can take numbers to objects as small as the elementary particles, like quarks and neutrinos, to those as big as the galaxies, the galaxy clusters, and eventually the whole universe itself, estimated to be about 93 billion light years in diameter. Now, 1 light year refers to the distance traveled by light in 1 year, and light travels at about 300,000 km per second. Or, if you're more familiar with scientific notation, 93 billion light years is about 10 to the power 27 meter. That is 1 followed by 27 zeros. Wow! And even more amazing is the fact that physics studies all this. Well, of course, to be exact, I should say that the different branches of physics and physicists study the universe at a different scale. Still, this is mind-blowing. Now, in this slide, there is a link. I strongly encourage you to open the site in your browser and explore the animation. Okay, so let's put all these scales in perspective. Where does fundamental of physics 1 reside in these scales? The horizontal axis refers to the size of the physical system we are dealing with. It gets bigger and bigger in the positive x direction, whereas the vertical axis refers to the speed of the system. It gets faster and faster in the positive y direction. Now, at the lower left corner, that is to say that when we are dealing with relatively very small tiny system, things at subatomic and atomic level, unobservable even by normal microscope, moving at relatively low speed, we are dealing with the so-called quantum system. This is a weird counterintuitive physical realm which is not the scope of this course. As the system gets bigger, things are becoming more, well, let's say comprehended, experienced. Things like ball falling, car moving, plane flying, water boiling, all the way to say mechanical evolution of the solar system, etc. These are phenomena which fall under the realm of classical physics, and this is where this course is dwelling in. What happens when your car moves faster and faster? Fast enough that it is comparable to the speed of light, 300,000 km per second. Well, physics at such super fast lane is governed by relativistic theory, developed by, I'm pretty sure you have heard his name before, Albert Einstein. This is again a weird counterintuitive realm where you could potentially manipulate the flow of time and so on. We will not talk about this at all in this course. Finally, it is now the subatomic particles zipping around at the speed of light we are talking about here. In the sense, it is like, well, quantum physics meets relativistic physics, and that becomes quantum relativistic physics. Do keep in mind that first, what I presented here is merely a quick guideline to categorize physics into branches. Each branch splits further into sub-branches, and more often than not, they are interrelated. Second, there is really no clear boundary between one branch to another. Where does exactly a system stop exhibiting quantum properties and behave classically, for instance? Well, it happens somewhere in the scale of 10 to the power minus 9 meter, or in the nanometer scale. Nano-objects such as carbon nanotube, graphene, or fullerene balls exhibit both quantum and classical behavior. A whole field of study called nanophysics or nanoscience is dedicated to study these objects. We also offer general education modules on nanoscience and nanotechnology here in NUS Physics Department. Finally, after going through all those, the last question we should address is, why is physics important? Here, I'm not going to talk about how engineer needs grounded knowledge in physics, or how the breakthrough of our knowledge of physics has shrunk down computer from the size of a lecture theater to the size of your palm. That is of course true, but that is cliché. Instead, why is physics important to you? How is this course relevant to you? Some of you may come from School of Computing, aspire to be the lead programmer in Blizzard Entertainment, or develop the Flappy Bird sort of hit with your startup. Either way, the message is straightforward. If you want to make a good, realistically looking game, you need to know physics. This little animation from Wikipedia delivers the point. How would a solid urn falling onto a solid inclined plane look like in the real world? Clearly, case number 4, which implements gravity, collision detection, and rotational dynamics of a solid object, will give audience a more realistic experience. A good detective needs a reasonable level of understanding in physics, among other skills. A murder case was mistaken as a suicide. Fortunately, Rod Cross, a physicist, saves the day. I recommend you guys to look up for his name in Google. He contributes not only in solving this murder mystery, he also actively promotes physics understanding through sport games such as tennis and baseball. Closer to home, I know at least 2 international level research labs in NUS, Mechanobiology Institute or MBI, and Center for Ion Beam Application or CIBA in short, which works at the interface between physics and cellular biology. Who says that biology is all about memorizing species names and molecular pathways? Even in the unlikely fields like sociology, business, and economy, physics has its contribution. The idea behind is to use physical theory and model to study the socio-economic behavior of a large population. Now you see, dealing with large number isn't a new thing in physics. 1 mole of, say, hydrogen gas, which is about 2 grams of H2 gas, consists of about 10 to the power 24, that is 1 with 24 zeros at the back, of H2 molecules. Yet physicists have developed a theory to compute the average kinetic energy of these individual molecules under certain temperature. And we are going to learn this in this course, under thermodynamics by the way. So surely we can lend some hands to our social scientist friends in dealing with the average behavior of 7 billion people. The list is definitely not exhaustive. I can go and on and on. 21st century is really an era of multidisciplinary study. And as long as it is a study involving material of physical world, physics will always play a role in one way or another. So that's all for now. Thank you for listening and stay tuned.